All right, we're going to go ahead and get started with lesson 10.10. This will be the last lesson that we'll do regarding Taylor series before we go ahead and begin our overall review for the AP exam. I'm very excited. Hope this gives you a little more practice thinking about and working with Taylor series. Okay, I want you to go ahead and try the warm-up problem. Take about 2-3 minutes. Do the warm-up problem. Pause the video, do the warm-up problem, then come back and check your work. All right, let's go ahead and take a look. Here it says we have the function f, and it satisfies this differential equation right here. Okay, this differential equation right here. And we know f of 0 is 3. The Taylor series for f converges to f of x for all x. Convenient. Find f double prime of 0, and find the second degree Taylor polynomial for f about x equals 0. So second degree Taylor polynomial, that means we will need this value and the first derivative value. Let's start working through this. So I know in the end I want my second degree Taylor polynomial, so I know f of 0, I will need that, is 3. F prime of 0 is going to get interesting here. F prime of 0, I'll use my formula up here. F prime of 0 is going to be equal to f of 0, because that's what my formula here says. Will be f of 0. F of 0 plus 2 times 0 minus 3. Okay. F of 0 is 3. Plus 0 minus 3. This actually gives us 0 here. Okay. So my second derivative, how would I get my second derivative at 0? Well, I have my first derivative. Based off of this then, if f prime of x is f of x plus 2x minus 3, that means my second derivative, if I just follow my derivative rules, it's going to be f prime of x plus 2. Derivative of 2x is 2, derivative of 3 is 0, so there we go. So I need f double prime of 0, which means this is going to be equal to f prime of 0, which I already found up here, plus 2. So it's going to be f prime of 0, which is 0, plus 2 gives us 2. So find the second derivative at 0. I just did right here, the second derivative at 0. And find the second degree Taylor polynomial for f at x equals 0. So my second degree Taylor polynomial is going to be, follow my pattern that we've always used, f of 0 divided by 0 factorial x minus a, which is 0 in this case, to the k, 0 power, plus 0 over 1 factorial, because I'm on my first derivative, x minus 0 to the first power, plus my second derivative is 2 over 2 factorial, because I'm on my second derivative, x minus 0 squared. And I can clean this up then, giving me p sub 2, my second degree Taylor polynomial, is equal to 3 divided by 1 times 1, so that'll be 3, plus 0 divided by 1 times x, so this will be 0. I'm not going to write that one then because this term will come out to be 0. And then 2 divided by 2, that's 1, times x minus 0, so that's just x squared. So here is my second degree Taylor polynomial for this specific function. All right, about x equals 0. All right, so hopefully that gives you a little warm up, getting the ball rolling again in your mind about how this stuff works. And today we're going to just keep practicing with our Taylor polynomials. All right. What I would like you to do for the following problems is I encourage you to, if you're feeling comfortable, to try them on your own, the 3 problems we're going to do, and then play the video to see how I do it. Taking the leap to kind of try these problems on your own, give them a shot even if you're not feeling 100% comfortable, is a good way to sort of flex your abilities and your muscles and get better and better over time. If you're still feeling like you'd rather just watch the examples and then practice in the homework, I would understand that too. Okay, let me go ahead and get started then. If you want to try this first one on your own, pause the video now. Otherwise, I'm going to get started. All right, let f be a function having derivatives of all orders. The third degree Taylor polynomial about x equals 2, okay, about x equals 2, is right here. Find f of 2 and f double prime of 2. All right. Okay. For this, it's probably worth remembering our old thing we've always been working off of for our Taylor polynomials, which is that our general formula for things in the Taylor polynomial is f of the kth derivative at a divided by k factorial times x minus a to the k, right? Right. I want f of 2. This is my Taylor polynomial at 2. So f of 2 would correspond to this very first thing here, to the thing that has x minus 2 to the 0th power, so this very first constant. So what am I going to say? I can say that f of 2 is divided by 0 factorial, because that's my 0th term, times x minus 2 to the 0 is going to be equal to that constant 7. This is kind of a long way to do it because we know that the f of 2 is going to come out to be 7 because that's the way these things always work, right? Because f of 2 divided by 0 factorial is 1, x minus 2 to 0 is 1, so we can very quickly see that f of 2 is just 7. That's how Taylor polynomials work. This first term represents just the constant value of the function at the value it's centered at. We can use a similar setup to find the squared term. Notice squared here. The second derivative using the squared term, because I know that the second derivative of f at 2 divided by 2 factorial times x minus 2. Actually, I guess let me back up for a second, because we don't actually need this, do we? Because all we're going to deal with here is the coefficient, because we want the derivative part of this. Same thing over here. I guess we just, better thing to say, actually, although it's true for that first one, better thing to say would be that, right? That the coefficient thing that we're looking at is equal to 7. For this first 0th term, it doesn't really matter that I included that last part because it was to the 0th power, but this would be correct, more generally speaking. So the second derivative at 2 divided by 2 factorial is going to be equal to whatever the constant I see in front here with its negative sign. There we go. So doing my quick math, 2 factorial is just 2, so f double prime of 2, I'm going to multiply 2 to this side, will give me negative 18. All right? And there are the two values that I am looking for. Okay. Let's go ahead and take a look at part B. All right. Part B asks something that we've not really quite seen yet, but is a good thing for making the connections between the different things we've learned this year in calculus. Part B says, is there enough information to determine whether f has a critical point at x equals 2? If not, explain why not. If so, determine whether f of 2 is a relative maximum, relative minimum, or neither, and justify your answer. Okay, so let's just start with our definition of a critical point. We can say if x equals 2 is a critical point. What's our definition of a critical point? A critical point is where the first derivative is 0 or does not exist, right? So if x equals 2 is a critical point, that means f prime of 2 is 0 or does not exist. Okay. F prime of 2. So let's go up to our Taylor polynomial because we know all the coefficients will tell us something about this derivative, f prime of 2. So I need to look for the coefficient of the thing that has x to the first power. Wait a minute. Is it x to the 0 power? Is it x squared? I don't have an x to the first power term. All right. I don't have that in here, and I would normally see that in a Taylor polynomial, which means that the first derivative value has to be 0. Since I'm missing that x minus 2 to the first power term, that means this derivative has to be 0. So is there enough information to determine this critical point? Yes. I can say f has a critical point at x equals 2. All right. Maybe the best way to say that is since, we can say since f prime of 2, which if we really wanted to, f prime of 2, this Taylor polynomial will tell us stuff about, what happens at x equals 2. I could take the first derivative of this and plug in. I could take the first derivative of this and plug into, and I would find that the derivative value would be 0. So I can say since f prime of 2, which would be equal to t prime of 2, is equal to 0. I therefore know that f does have a critical point at x equals 2. Now, is there enough information to determine if f of 2 is a relative maximum, minimum, or neither. Remember, if we know there's a critical point, to determine a min-max at a critical point, we need the second derivative. All right? Because the second derivative will tell us, okay, I know I have a critical point. Is my graph concave down from there? In which case, if it's concave down, my second derivative will be negative, and I'll have a maximum, things like that. All right, so let's go ahead and say, okay, looking here, let me figure out what is my second derivative. What do I know about f double prime of 2? What do I know about that, the second derivative there? And based off of our work for part A, we actually know some information about the second derivative at 2, right? The second derivative at 2, I found out, is equal to negative 18, all right? Second derivative of 2 is equal to negative 18, which is less than 0. I can say, therefore, f of 2 is see, the second derivative is negative, which means my graph is concave down. That means f of 2 is a maximum, is a relative maximum, maybe is a more accurate thing to say. F of 2 is a relative maximum because f double prime of 2 is negative, right? And then in my head, I remember if f double prime of 2 is negative, that means my graph is concave down, which means my f of 2 has to be a maximum. So since the second derivative is less than 0, is negative, f of 2 is a relative maximum value. All right? Okay, not too bad. Let's move on to the next part then. All right, part C. Part C says use t of x to find an approximation for f of 0. Let's just do that part first. So that means we need t of 0, because the Taylor polynomial is going to approximate f. So t of 0 would give us 7 minus 9 times 0 minus 2 squared minus 3, 0 minus 2 cubed. What is this going to give me? This is going to be 7 minus 9 times, that's negative 2 squared, so that's 4, minus 3 times negative 2 to the third, that's 8. All right. You don't have to simplify stuff, but we will here. So this gives us then 7 minus 9 times 4 is 36. Oh, sorry, this should be negative 8, shouldn't it? Because it's negative 2 cubed. This will be plus then 3 times 8. Negative 3 times negative 8 will be plus 24, which is going to give us negative 36 plus 31, which will give us negative 5. Negative 5 then is our approximation for f of 0. So we can say f of 0 is about negative 5. That should be a 0. F of 0 is about negative 5. Okay, so that's the first part of this. Let's see what they ask us to do next. All right, f of 0 is approximately negative 5. Is there enough information given to determine whether f has a critical point at x equals 0? If not, explain why or why not. If so, determine whether f of 0 is a relative maximum, minimum, neither, and justify your answer. So it sounds very similar, right? But here's the deal. Notice here they're asking us about x equals 0. So we go, okay, all this information up here, what is it based around? It's based around x equals 2, right? My derivatives and my values up here are all going to come around x equals 2. Do I have enough information to figure out what's going on at x equals 0? The answer here is no. It is not possible. It is not possible to determine. It's not possible to determine if f has a critical point at x equals 0. Because, probably the best way to say this is because t of x gives exact information, only at x equals 2, right? Only at x equals 2, because these values and these derivatives were arrived at by using x equals 2. X equals 0 is nearby. This information is not going to be as useful for that and will not tell us like exact values about things at x equals 0. Okay? It is not possible to determine if f has a critical point at x equals 0 because t of x gives exact information only at x equals 2. Hopefully that helps clarify some of that. I like this problem because it gets us thinking about how we can apply our understanding of the values in here to some of the other information we've learned already in calculus. Okay? Cool. Let's move on to the next one. Again, if you want to, you can pause, give this problem a shot, and then come back and check your work. Or if you would like, you can also just have me explain through it as we go if you're feeling less comfortable. I do encourage you to just give it a shot first. All right. The Maclaurin series, e to the x is e to the x equals 1 plus x plus blah, 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 blah. This is one you also need to memorize because they don't always just like throw it at you like this. This is one of the ones that'll be on the quiz on Wednesday. The continuous function f is defined by, okay, we have this function f, which is a little more complicated when x is not 1, but that makes sense. And f of 1 is 1, and we do know that. The function f has derivatives of all orders, okay? Right, the first 4 non-zero terms, and the general term for the Taylor series for e to the x minus 1 squared, okay? So we have e to the x, they give us that. We know it, so I'm just going to kind of copy it down. E to the x equals 1 plus x squared over 2 factorial, in this case 2, plus x cubed over 3 factorial, which is 6, plus so on and so forth, plus x to the n over n factorial, plus so on and so forth. We want to write the first 4 non-zero terms and the general term for the Taylor series for e to the quantity x minus 1 squared about x equals 1. Okay? All right. So what do we need to do to make this happen? We can base it off of what we know about e to the x, right? We know how e to the x works. It works like this. So we can go ahead maybe and say this then. All right. If I'm going to replace this x, the only difference I'm replacing this x with x minus 1 squared. So I can say e to the x minus 1 squared is going to be equal to 1 plus, I'm going to replace all these x's with x minus 1 squared. X minus 1 squared plus x minus 1 squared squared. X minus 1 squared squared, so that'll be x to the minus 1 to the 4th over 2, plus x minus 1 squared, we'll go in for x cubed, so that'll give me x minus 1 to the 6th over 6, plus, all right, that's what do we want? We want the first 4 non-zero terms. So there we go. There's the first 4 non-zero terms, plus dot dot dot, plus. All right, how did this inside part change? Okay, what are we looking at for our general rule here? Our general rule here then is going to be x minus 1. Remember, this is the 0th term, this is the first, this is the second, this is the third term. So it looks like we're taking the term number and multiplying it by 2. So this is going to be x minus 1 to the 2n over, the denominator still stayed the same, and that was n factorial in our originals here. So this is over n factorial plus dot dot dot. Then we stand back and sort of check our work here. All right, 1 plus, I plugged in x minus 1 squared for each of my x values. Double check, make sure I did all my squaring and things right. All right, there we go. Looks pretty good. This is our Taylor series for e to the x minus 1 squared about x equals 1. Okay? Cool, let's move on to part B. Part B looks like it is going to build off of that a little bit. B, use the Taylor series found in part A, the one we just came up with, which I'll write down again. Our Taylor series in part A, we said e to the x minus 1 squared was going to be equal to, we said 1 plus x minus 1 squared plus x minus 1 to the fourth, right, over 2 plus x minus 1 to the sixth over 6 plus dot 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 plus, that is x minus 1 to the 2, the 2n we said, over n factorial, and so on and so forth, right? Clean this up a tiny bit. All right. So that's what we have. That's what we had after part A. It says use this Taylor series found in part A to write the first 4 non-zero terms and the general term for the Taylor series for f. And f, I know here. All right, I know f here about x equals 1. Well, that's what we already wrote this for, right? So that seems to line up. So what do we need to do to go from this to get to this thing here? Well, I have the e to the x minus 1 squared part already. I need to subtract 1, and then need to divide by x minus 1 squared. So I can do that kind of in stages. Let me just say, okay, I'm going to start manipulating this. I want e to the x minus 1 squared minus 1. I want to subtract that. So I'm going to subtract 1 from this side. It's going to give me x minus 1 squared plus x minus 1 to the fourth over 2 plus x minus 1 to the sixth over 6 plus so on and so forth plus x minus 1 to the, this is going to be interesting here because now my terms, I kind of got rid of that first term, so this is my 0th term here. So I kind of need to shift these back. I want my 0th term to start at 2. So I want to say, it's still counting up, by even numbers only, so it's still going to be 2, but instead of, because this is my 0th term now, instead of 2 times n, it's going to be 2 times n plus 1, because when n is 0, I need to start with a squared. So 0 plus 1 times 2, that'll work, all over. All right, this is my 0th term. This is my first term. So I kind of need to do the same thing down here, don't I? I need to do n plus 1 factorial, because of the 0th term I need to divide by 1. So 0 plus 1 factorial give me 1. At my first term I need 2 factorial. So that'd be 1 plus 1. Yeah, so this will work. Okay. What else do I need to do? I need to divide everything now by x minus 1 squared. So I can do that. This will be e to the x minus 1 squared minus 1. Divide everything by x minus 1 squared. So I'm going to do that to everything in here. I'm going to divide everything by x minus 1 squared. X minus 1 squared divided by x minus 1 squared is going to be 1. Plus divide this by x minus 1 squared. It's going to take 2 x minus 1 factors out of the top. So that's x minus 1 squared now, because I'm dividing a squared into this, over 2. Plus, I'm going to divide an x minus 1 squared into this, so it's going to lose 2 out of there. This will be x minus 1 to the fourth over 6. So then I got to think through, okay, what's my general term now? Okay, so this is my 0th term. This is my first term. This is my second term. So what's my general rule now? My general rule looks like it still has an x minus 1. X minus 1. My first term has a squared, so it looks like I can go back to calling this 2n, because my 0 first term, second term has a 4, so 2 times 2 would give me to the 4th power, over 0th term, first term looks like it's still 2 factorial, second term is 3 factorial, so it looks like I still need n plus 1 factorial. Remember, you can always check these things by just plugging in, okay, n equals 0 is my first thing I'm looking at here. So when n is 0, I get x minus 1 to the 0 power. That's 1 over 1 factorial, so that should give me 1. My n equals 1 term over here needs a squared power, so that would happen over 2 factorial. That would happen down there. So this looks pretty good. Oh, don't forget these things should keep on going. So kind of stood back and checked our work. Let's make sure we answered the whole problem. We need to write the first four non-zero terms. We actually haven't done that yet. Sorry, right? The first 4 non-zero terms. We haven't actually done that yet. So let me go ahead and add that in. Remember, we always want to make sure we actually answer the question at hand. So I'm going to go back in here. We can continue this pattern. Then this would be plus. This guy would be x minus 1 to the 6th power over, this was 2 factorial, this was 3 factorial, this one's going to be 4 factorial, so that's 4 times 3 times 2, so that'll be 24 plus so on and so forth plus. Okay, let's make sure we answer the question now, right? The first 4 non-zero terms and the general term for the Taylor series for f. All right, it looks pretty good now. I think we got everything we need. Just doing one last check, right? Make sure you haven't written a number down wrong, especially with so many different numbers and things to keep track of. All right, looks pretty good. There we go. There's part B. All right, let's take a look at part C. Part C says, use the ratio test to determine the interval of convergence for the Taylor series found in part B. Ratio test. We know how to do that. We already found, right, what our general term is. Our general term for this series, if we kind of do our summation notation, our general term for this series, we said was x minus 1 to the 2n over n plus 1 quantity factorial, right? That was our general term. And we know for our ratio test, the ratio test says we want the limit as n approaches infinity of n plus 1 in this thing over this thing. So we can say then that's x minus 1 to n plus 1 over n plus 1 plus 1. So that'll give me n plus 2 factorial. It would be divided by this thing, evaluated at n. But dividing by this is the same thing as multiplying by the reciprocal. So I'm just going to go ahead and write in n plus 1 factorial over x minus 1 to the 2n. We want the limit as n approaches infinity of this thing. All right. Do some cleaning up here. This is going to be the limit as n approaches... Oh, forgot my absolute value signs, didn't I? This is going to be the limit of the absolute value of this thing. Limit of the absolute value of that thing. The limit of the absolute value of x minus 1 to the 2n plus 2, 2n plus 2, over n plus 2 factorial times n plus 1 factorial over x minus 1 to the 2n. All right, I think we're ready to do some good work here now. So what is this going to be equal to? We can do some simplifying as we've seen before with ratio test. X minus 1 to the 2n plus 2, x minus 1 to the 2n, so we'll lose the x minus 1s to the 2n. It'll leave us with x minus 1 squared, so I can write that out. The limit as n approaches infinity of the absolute value of x minus 1 squared will be left. X minus 1 to the 2n, we'll lose both of those. They'll divide away. X minus 1 squared. Now, my factorials are interesting. N plus 1 factorial, n plus 2 factorial. N plus 2 factorial, if you kind of think about it, is really n plus 2 times n plus 1 times n times all those things. So this is really n plus 2 times n plus 1 factorial. So my n plus 1 factorial I'll lose. I'll lose the n plus 1 factorial down here, leaving me with just n plus 2 down there. N plus 2 will be left in the denominator down there, okay? There is my limit. Okay, and I know that if I want this limit here in my ratio test, right? I'm looking for my ratio test, and we got all these different kinds of uh, tests we got to keep in mind. But for our ratio test, we need to remember that when we do this ratio and we find the limit, that if the limit is less than 1, then we know something, right? In this case, the limit is, let's evaluate it, as n approaches infinity. Does it matter what x is? No, x is, we're going to kind of treat like a constant. As n approaches infinity, the denominator is going to grow. So this limit, no matter what x is going to be 0, right? And so for our ratio test, we found that our limit 0 is less than 1. Which means that our series up here is going to be convergent, and it doesn't matter what x is. So what can we say about this? We can say then, because ultimately this question is asking us about the interval of convergence, it doesn't matter what x is. We can then say, therefore, the interval of convergence is, we just say like negative infinity to infinity. It doesn't matter what the x value is in this case, because this ratio test as n goes to infinity is going to destroy whatever this value is up here, because n is going to grow. So this series will always be convergent for all x's, so the interval of convergence is negative infinity to infinity. All right. And part D. We want to use the Taylor series for f about x equals 1 to determine whether the graph has any points of inflection. All right, I'm going to write out what I know for my Taylor series, the one I already wrote, that f of x is going to be equal to, what did I write out? I said it was 1 plus x minus 1 squared over 2, right? X minus 1 squared over 2 plus x minus 1 to the 4th over 6 plus x minus 1 to the 6th over 24 plus, I'm not going to write out, the rest of the stuff right now, but there we go. That's what we found out x was, right? And here we're asked, use the Taylor series to determine whether f has any points of inflection. Well, points of inflection, that's a second derivative question, right? Ultimately, points of inflection is a second derivative question, okay? So let's find the second derivative. The first derivative is going to be, the first derivative of 1 is 0. We're just going to do term-by-term differentiation. The first derivative here, bring down the 2, is going to cancel out with that 2. It'll give us x minus 1. Plus, bring down the 4. That'll give us 4x minus 1 cubed over 6. Don't have to worry about chain rule because the derivative of the inside is just 1. Plus, bring down this. That'll be 6x minus 1 to the 5th over 24, and so on and so forth for all the other derivatives. I want to get down to the second derivative. The second derivative of x minus 1 is just 1, plus the derivative over here, bring down the 3. That'll give me 12, x minus 1 squared over 6, plus bring down this 5. That'll give me 30, x minus 1 to the 4th, right? Over 24 plus blah, 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 blah. Okay, so here's what I'm looking at for my second derivative. Use the Taylor series to determine whether or not f has any points of inflection. Well, I know points of inflection are going to happen when the second derivative of x changes sign. All right, and I just took the second derivative of f, so I can go, hey, is this thing going to change sign anywhere? If so, where? Well, let me look at the values here, positives, negatives. This is positive. Plus 12 over 6, x minus 1 squared. Well, it's got a squared, so that's always going to be positive. Plus 30 over 24, x minus 1 to the 4th. That's always going to be positive. And this pattern will continue. Every term in here is going to be positive. All right? If you actually write out the general term here for what we just did, we found out, if you did this for your general term, you would find out that our value would be 2n minus 1, because we just brought down 2 power rule power things, x minus 1 to the 2n minus 2 over n plus 1 factorial. That's our general rule for our second derivative. You didn't actually need to find that, but it can help prove to you, if you're kind of feeling stuck about this, why this thing will always come out to be positive. Our second derivative then is always going to be positive. 1 plus a positive thing plus a positive thing. So if points of inflection when the second derivative changes sign, and we're asked, determine if the graph of f has any points of inflection, we found out that the second derivative is always going to be positive. We can say f has no points of inflection because, and why? Every term in f double prime of x is non-negative. Maybe it's a good way to say that, is non-negative. Every term in f double prime is non-negative. What does that mean? That means the second derivative of x is going to be greater than or equal to 0 for all x. All right, doesn't matter what x value you put in. And there we go. F has no points of inflection because every term in f double prime is non-negative. That means f double prime is greater than or equal to 0 for all x. All right. Pretty good question. Here again, connecting to points of inflection and things we have learned earlier this year. You can always do term-by-term differentiation. All right. Let's take a look at one more. Okay. We're going to look at two parts of this one again. You can pause it now, try the problem, come back and check your work, or you can watch me do it right now. Okay. So we're given, we're told that the Maclaurin series for natural log of 1 plus x is given by this thing. Okay, that's kind of helpful. Remember, there's certain Maclaurin series you do need to memorize. Please make sure that happens. On its interval convergence, this series converges to a natural log of 1 plus x. Let f be the function defined here. And we want to know write the first four non-zero terms in the general term for the Maclaurin series for f. Remember, Maclaurin series is a Taylor series centered at x equals 0. So, let's see. A. We want to write the Maclaurin series for f. F looks a whole lot like what they give us up here. So let's do what we've done before in some of our previous problems. Let's copy down what we know. The natural log of 1 plus x, right, is going to be equal to the series they give us here, 1 minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus so on and so forth plus negative 1 to the n plus 1 x to the n over n plus and so on and so forth to infinity. Okay. We need to make this series down here look like this one. So we have some things to do. Let's do it step by step like we've done before. All right, let's go ahead and first replace our x with x over 3. So this will be natural log of 1 plus x over 3, which means replace every x value with x over 3. Okay, so this will be x over 3 minus x over 3 squared over 2 plus x over 3 cubed over 3 minus x over 3 to the 4th over 4 plus so on and so forth plus negative 1 to the n plus 1 x over 3 to the n over n plus so on and so forth. Okay. Okay, I replace my x with x over 3. What else do I need? I need to then multiply everything by x. Okay, so this would be x times the natural log of 1 plus x over 3, which will be equal to, I'm going to multiply this whole thing I just wrote out by x and see what I get. So this would be x squared over 3. And I keep going. I'm going to go ahead and do some like cleaning up here as I work. So this is going to be minus. This would be x squared over 9 times x over 2. I'll come back to that a little later. Plus, this is going to be x cubed over 27 times an x, because I'm multiplying everything by x now. This part came from my parentheses up here, over 3. Minus, that would be x to the 4th over 3 to the 4th is going to be 81. But then that whole quantity I just found out was right there, times x, I'm multiplying everything by x, over 4, plus so on and so forth, plus negative 1 to the n plus 1 times, this is going to be x to the n over 3 to the n times x, all over n plus so on and so forth. So this is actually, this is what we're looking for, the first 4 non-zero terms and the general term, but it looks kind of goofy and silly right now. So I'm going to take the time here and make this look a little neater. Okay, I'm going to make this look a little neater. You actually just excuse this for a second. I'm going to back up some of this stuff so I can have a little room to write this out. It might run over a little bit, so I'm sorry. So I'm going to take this up here, give myself a little more room actually than that. All right, so I'm going to take this, and let's go ahead and clean up this. What does that mean that final answer is equal to? X squared over 3 stays as x squared over 3. Nothing really we can do to that. Minus, this will be x cubed over, I'm dividing by 2, so I'll multiply in there. This will be x cubed over 18, right? 9 times 2. Plus, all right, this is going to be, my next one here is going to be x to the 4th. X to the 4th over, multiply that 3 into that 27 is going to be 81. Minus x to the 5th, x to the 4th times x will be x to the 5th over 4 times 81. 4 times 81, if you actually want to write that number out, we know where each of those numbers came from at this point, but 4 times 81, the actual value is 324. So we could write that out, 324 if we want, 324 comes from there, plus so on and so forth. Plus, we can clean this up a little bit here. This is going to be negative 1 to the n plus 1. Oop, my n plus 1 kind of hasn't changed, right? That's a weird looking n plus 1, though. We probably should change at that point. N plus 1. Trust me, that's an n plus 1. And then I have x to the n times x. So I'm going to combine, that's x. I'm going to add my exponents, so that x to the n plus 1 over n times 3 to the n is going to be my general term denominator down there. Remember, if you're afraid of simplifying errors, which is fine, you can just leave things like this. That's this legitimate as well. I just want to get you sort of the cleaned up look. I would recommend leaving it like this, though. All right, so there are my first 4 non-zero terms and my general term for my Maclaurin series for f. All right, let's look at part B. Okay, part B. Now it says determine the interval of convergence of the Maclaurin series for f. The interval of convergence for the Maclaurin series for f that we just found. Show the work that leads to your answer. All right, interval of convergence. One of the easiest things, as we have seen, to find interval of convergence is actually to use our ratio test. We saw that already today. So let's go ahead and do that for this. We have our general rule, which we already saw was negative 1 to the n plus 1. So our series really is n equals 0 to infinity of negative 1 to the n plus 1 times the quantity x to the n plus 1 over n times 3 to the n. Remember, our ratio test says take the limit as n approaches infinity of the absolute value of all these things, but at n plus 1. So that will make this negative 1 to the n plus 1, but n plus 1 plus 1. So that'll give me n plus 2. N plus 2. Sorry about that. N plus 2. And then I would have x to the n plus 1, but that's n plus 1 plus 1 because I want to go up 1 for my ratio test. So that'll be n plus 2 all over n plus 1 times 3 to the n plus 1. And I would typically divide this by my original series, just my to the n kind of thing, my nth term. But dividing by this is the same thing as multiplying by its reciprocal, so I'll do that. That's n times 3 to the n over negative 1 to the n plus 1 times x to the n plus 1, the absolute value of all that. I can simplify this limit, the limit as n approaches infinity of, got a bunch of things that I'll cancel out here, which will be kind of nice. Negative 1 to the n plus 2, negative 1 to the n plus 1. I'll lose most of that and be left with just negative 1 to the n plus 2. N plus 1 will be negative 1 to the first power would be all that's left. X to the n plus 2. This is x to the n plus 1, so we'll lose n plus 1 and n plus 1, which will leave me x to the first power up there also. So I've simplified those things. N plus 1, there's no way to simplify that with this n, so that's still going to be over n plus 1. And I would have an n left up on top. But then 3 to the n plus 1, 3 to the n, my 3 to the n's will cancel out, leave me with a 3 down there. So what is this? The limit as n approaches infinity of the absolute value of, I can simplify kind of all this together, negative 1 times x the first times n. So that'll give me negative n times x over, I'll distribute that 3 in there, 3n plus 3. If I think about my n behavior model then, negative n, well, I'm going to take the absolute value of this, right? So I don't really need to even actually worry about that negative. So this is going to be the limit as n approaches infinity. X is, we will need to keep the absolute value sign around x because x is kind of an open term here. So I'm going to rewrite this then as n times the absolute value of x. Took the absolute value of that negative sign, so n times the absolute value of whatever x is, over the absolute value of 3n plus 3, but n is going to be positive, so I'm just going to leave this as 3n plus 3. I can now think about my n behavior model then. N times the absolute value of x is going to win. N times the absolute value of x is going to win up top. Oop, got to leave room for my limit. Can't forget your limit. This is going to be the limit as n approaches infinity, right? N times the absolute value of x is going to win up top. 3n is going to win down here. So what does this mean? For the ratio test to give us something that converges, this limit has to be less than 1, right? This limit has to be less than 1. Okay? As n approaches infinity, n and n, those will have the same power, so those will be equal to each other and essentially divide away, and we'll be left with this. We'll be left with the absolute value of x over 3 has to be less than 1. So what does that mean for us? That means the absolute value of x has to be less than 3. So what does that mean for us? So the absolute value of x has to be less than 3, which means that x has to be between negative 3 and 3, right? We want the interval of convergence. The interval of convergence, in this case, is negative 3 to 3. If they ask us about the radius of convergence, the radius of convergence is 3. All right, so take a look at that for a second. Go back, double check. That's what I'm doing right now. You always want to make sure you've done everything correctly. All right, so what we would need to do at this point, which I'm not going to cover here, so I did state that this is true, that the interval of convergence is -3 to 3 non-inclusive. What I'm not going to end up covering here is why it is non-inclusive. That is for a different day, and given the sort of scope of this year's test, is not something that's on there, so I won't be discussing why it's non-inclusive. But this at least shows us that the radius of convergence is 3. But this is true. -3 to 3 would be the interval of convergence, non-inclusive. If you do want to do a quick test, you can go ahead and check what happens to our series when x is 3 and use your different test to determine what's going to happen there. And when x is -3, you can find it diverges by comparison to the harmonic series. And when x is +3, you can use the alternating series test to show that it diverges at 3. So we're not going to include -3 and 3 in our interval of convergence. If you have questions, email me. We can talk about those, but that is sort of outside of the scope of what we're going to do right now for this year. And we'll cover that stuff after the AP exam. All right. Take care, everybody. Please make sure for homework that you do get a chance to try the 2 problems below. 2 more for your response questions, and then follow the same steps as the weekend. Do them, make your corrections, and submit your score report. All right. I'll see everybody later. Bye.